Good morning, class! I am Teacher Merlin from Tangub City Global College. Are you guys ready for another math exciting lesson for today? So am I. But before we begin, I want you to say these words. Math is fun. Say it with me. Again, math is fun. But before we begin our lesson, take a look at the board. What do we have here? Oh, a clock! Wow. Did you know that clocks are actually related to our lesson for today? Keep your answers in mind because we are going to get back to it later. Let's begin by remembering what an Euler's theorem is. Euler's theorem states that for every positive integer a and n, which are said to be relatively prime, then a raised to the power of v of n is congruent to 1 mod n. But before we delve to Euler's theorem, let us first define what an Euler's quotient theorem is. Euler's quotient theorem is denoted as v of n. And v of n is the number of positive integers less than n which are relatively prime to n. To further understand what is an Euler's quotient theorem is, let us have an example. We have here example 1. Find phi of 5. To solve phi of n, let us first identify what is n. Since in the given example we have phi of 5, then our n is equal to 5. Since phi of n are the positive integers less than n which are relatively prime to n, let us first identify the numbers less than 5. Remember that this number must be positive integers. So we have 1, 2, 3, and 4. After that, we will identify if these numbers are relatively prime to n, which is 5. And relatively prime means that their GCD, or the greatest common denominator, is only 1. Wow. So, 1 and 5, the GCD of 1 and 5 is 1. For 2 and 5, we also have 1. For 3 and 5, we have 1. And for 4 and 5, we also have 1. Therefore, 1, 2, 3, and 4 are all relatively prime to 5. Since there are 4 less than 5 that are relatively prime to 5, therefore, phi of 5 is equal to 4.
Very good.
As now then proceed to our example 2. We have here find phi of 11. First, we will identify what is n. And from the given example, n is equal to 11. Next, we are going to list the numbers less than 11. Always remember that these numbers must be positive integers. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Then, we will identify if these numbers are relatively prime to 11. The GCD of 11 and the numbers 1 to 10 is 1. Therefore, these numbers are relatively prime to 11. So that means that phi of 11 is equal to 10. Meaning, there are 10 numbers less than 11 that are relatively prime to 11. But how about if n is a big number? How are we going to get the phi of n? Don't worry, because we are going to discuss 3 formulas that will make our lives easier and solve phi of n. Case number 1. If n is a prime number, all you have to do is to subtract it with 1. So phi of n will be equal to n minus 1. Case number 2. If n is a composite number, so that would be n is equal to p times q. Remember that p and q must be prime numbers. So the formula that we will be using is phi of n is equal to the quantity of p minus 1 times the quantity of q minus 1. But how about if n is a composite number and one of the factors is a composite number too? What are we going to do? Don't worry, because we have case number 3. The formula that we will be using is phi of n is equal to n times the quantity of 1 minus 1 over p sub 1 times the quantity of 1 minus 1 over p sub 2, and so on, depending on how many factors are we using. To further understand the 3 cases of Euler's Taussian theorem, let us have an example. First example, find phi of 5. First, we are going to identify what is n. N is equal to 5. And we all know that 5 is a prime number. So what case or formula are we going to use? Very good! Case number 1. And the formula for case number 1, if n is a prime number, phi of n is equal to n minus 1. All we have to do is to substitute the given values. So that would become phi of 5 is equal to 5 minus 1. And 5 minus 1 is equal to 4. So, phi of 5 is equal to 4. Meaning there are 4 positive integers less than 5 that are relatively prime to 5. Is that understood, class? Very good. Now, let us proceed to example number 2. And for the example number 2, we have find phi of 35. First, we are going to identify the value of n. For this example, n is equal to 35. And we all know that 35 is a composite number. And 35 has 2 positive prime factors, which are 7 and 5. Let us now then assign 5 as our p and 7 as our q. So that would be phi of n is equal to the quantity of p minus 1 times the quantity of q minus 1. So that would become phi of 35 is equal to the quantity of 5 minus 1 times the quantity of 7 minus 1. 5 minus 1 is equal to 4 and 7 minus 1 is equal to 6. So that would become phi of 35 is equal to 4 times 6, and 4 times 6 is equal to 24. Therefore, phi of 35 is equal to 24, meaning there are 24 positive integers less than 35 that are relatively prime to 35. Is that understood, class? I believe that you all understood because you are smart students. Wait, there's more. We still have example number 3. And for example number 3, we have phi of 1,000. Oh, that is a very big number. First, we are going to identify what is n. N is equal to 1,000. That is a very big number. So what case are we going to use? That's great.
Very
Case
good.
number 3. We have if n is a composite number and one of the factors is a composite number, we will use the phi of n is equal to n times the quantity of 1 minus 1 over p sub 1 times the quantity of 1 minus 1 over p sub 2, and so on depending on how many factors. Since 1000 is a composite number, we will now then use the case number 3. Now, let us identify what are the factors of 1000. Great! We have 125 and 8. Let us now then identify the distinct factors of 125 and 8. For 125, we have 5 cubed, and for 8, we have 2 cubed. Therefore, the distinct factors of 1000 is 2 and 5. Let us now then substitute the given values to our formula. Again, the formula for case number 3 is P of n is equal to n times the quantity of 1 minus 1 over p sub 1 times the quantity of 1 minus 1 over p sub 2, and so on depending on the number of factors. Since we only have 2 distinct factors, so we will just end at p sub 2. So now let us substitute the given values. So we will have phi of 1000 is equal to 1000 times the quantity of 1 minus 1 over 2, our first distinct factor, which is 2, and 1 minus 1 over 5, which is our second distinct factor. Since 1 minus 1 half is equal to 1 half, and 1 minus 1/5 is equal to 4/5, so that would become 1000 times 1/2 times 4/5, and that would become P of 1000 is equal to 1000 times 1/2 times 4/5, and the result is very good, 400. Therefore, P of 1000 is equal to 400, meaning there are 400 positive integers less than 1000 that are relatively prime to 1000. So is that understood, class? Do you still have any questions or clarification with regards to the 3 cases of Euler's Gaussian theorem? So, hearing none, let us now go back to our main topic, which is the Euler's theorem. Arap na! Do you still remember the formula for the Euler's theorem? Very good. We have a raised to the power of p of n is congruent to 1 mod n. Let us have example number 1. We have to prove Euler's theorem holds true for a is equal to 3 and n is equal to 10. By substituting the given values to our formula, that would become 3 raised to the power of p of 10 is equal to 1 mod 10. To solve this example, let us first solve p of n. What case are we going to use? Very good! Case number 2. Since 10 is a composite number and it has 2 prime factors, which are 2 and 5, we will now then substitute the values to the formula. So that would become 5 minus 1 is equal to 4, and 2 minus 1 is equal to 1, and 4 times 1 is equal to 4. Therefore, P of 10 is equal to 4. But it's not the end. We will now proceed to the overall formula of the Euler's theorem. 3 raised to the power of is congruent to 1 mod 10. And 3 raised to the power of 4 is equal to 81. So that would become 81 is congruent to 1 mod 10. And 81 is congruent to 1 mod 10 is true. Since 81 mod 10 is equal to 1. For it holds true for a is equal to 3 and n is equal to 10. Is that understood, class? And now let us proceed to our example number 2. Does Euler's theorem hold true for A is equal to 2 and n is equal to 11? And we all know that the formula for Euler's theorem is A raised to the power of v of n is congruent to 1 mod n. Now let us substitute the given values. So we will have 2 raised to the power of v of 10 is congruent to 1 mod 10. Since we all know that v of 10 is equal to 4, then we will have 2 raised to the power of 4 is congruent to 1 mod 10. And 2 raised to the power of 4, the result is 16. So the question is it true that 16 is congruent to 1 mod 10? Yes or no? Very good. No, because 16 mod 10 is equal to 6. Therefore, 16 is not congruent to 1 mod 10. And it does not hold true for Euler's theorem if A is equal to 2 and n is equal to 10. Euler's theorem does not hold true for A is equal to 2 and n is equal to 10. So, going back earlier, clocks and Euler's theorem are connected by the concept of remainders. Clocks wrap around after a certain time, like 12 hours, which is similar to finding the remainder after dividing by 12. Euler's theorem deals with remainders when numbers are raised to powers. So the cyclical nature of clocks relates to the mathematical principles behind it. Great job, class! I hope you learned from our new lesson for today. See you next meeting!